Hey team, I'm Maddie. Welcome to Science Side Up. Today we're gonna start talking about climate feedbacks by talking about the Ice Albedo feedback. So far in our discussion of climate dynamics, we've really only talked about the Earth as a whole. We've talked about how CO2 rising is going to affect global temperature. We've understood how we get that temperature balance from our incoming solar radiation, but everything we've talked about has been about the Earth as a whole. What we're going to start doing now is talk about regional climate change. So one of the ways that different regions are affected differently by a global rise in temperature has to do with climate feedbacks. Climate feedbacks are feedback loops. So a positive climate feedback means that process causes temperature to warm more. A negative climate feedback would be one that dampens the effect of global warming. Over the next several videos, probably 4, we're gonna talk about ice albedo feedback, water vapor feedback, cloud feedbacks, and CO2 feedback. But for today, we're gonna talk about what is, at least in my mind, the simplest of the feedback loops, and that is the ice albedo feedback. I might think it's the simplest because it has to do with the polar regions, and that's what I do for my PhD. I think about the polar regions all day, every day. So that's probably why this is my favorite. The Ice Albedo Effect, spoilers, has the biggest impact where you have the most ice. So this really affects the polar regions and isn't that big of a deal in the tropics or the mid-latitudes, especially not in the tropics. We've talked before about albedo, but just as a quick refresher, remember that albedo is sort of how shiny a surface is. It's looking at how much incoming sunlight is just reflected straight back to space. So a perfect mirror would have an albedo of 1. Something that was not shiny at all would have an albedo of 0. Is that the wind creaking my house, or is someone breaking into the garage? We'll never know. A good number for Earth's average albedo is about 0.3, but it actually varies a lot globally. Here is a lovely graph of what albedo looks like across the Earth. I grabbed this from NASA's Earth Observatory website, and there's a link in the description if you want to check it out for yourself. What I want you to notice is that we generally have lower albedo near the equator in the tropics and higher albedo near the north and south poles. What that means is less sunlight makes it to the surface at the pole because of that ice, because it's so shiny and reflects things back to space. So let's draw what this climate feedback looks like. We're gonna start with a box. This box is surface temperature. Surface temperature is going to affect ice coverage. Ice coverage affects albedo, and albedo in turn affects absorbed sunlight. Now let's think about what happens when surface temperature goes up. Up arrow. So if surface temperature goes up, ice coverage should go down because we have less melting. So if this goes up, this goes down. That means we have a negative relationship between these two guys. So I'm gonna draw that with a red line, and I'm gonna end it with a circle. So if you're looking at climate feedback diagrams in the wild, circles refer to this negative relationship, and an arrow refers to a positive relationship. I'm using red and green to make that pretty visually clear, negative versus positive. But I want you to be able to read a climate feedback loop chart on your own if you so desire. So back to this. If ice coverage goes down, we have less ice, so we're less shiny. That's gonna make albedo go down. So the important thing here is that these two guys, ice coverage and albedo, will change in the same way, which means it's a positive relationship. So positive versus negative is just, do they change in the same way for positive? Do they change in different ways for negative? Great. So if our albedo goes down, we're less shiny, more sunlight is gonna make it to the surface. Boop. So this is gonna go up. Note that we have a net negative relationship here. So we're gonna go this way. Boop. And if absorbed sunlight goes up, then surface temperature also goes up. So we get a positive relationship here. So if we follow this loop all the way around, the whole process says when surface temperature goes up, the ice albedo effect causes surface temperature to go up even more. So this is a positive, net positive feedback loop. A flowchart on a chalkboard is all well and good, but is this a process we see in real life? Is this something that we can measure and observe? Absolutely it is. The Arctic is warming at twice the rate of the rest of the planet. So here is a graph of global heating rates. I'm sorry that looks like the color bar got cut off there for you guys. And I snagged this image from a Stanford pop sci kind of article. Link is in the description. But the thing to take away from this is notice all of those bright pink colors. Our fastest heating rates are in fact at the poles and mostly at the Arctic. So we can see in data this increased heating rate at the poles because of the ice albedo effect. And just in case you thought this was really simple, there are other processes going on at the Arctic, so that doubling of heating rate isn't only from the ice albedo effect, but it is mostly from the ice albedo effect. Okay team, that's all I've got for you today. Come back next week. We'll start talking about other climate feedbacks and really wrap our heads around these regional differences in what climate change looks like. Until then, please like, subscribe, don't forget to be kind, and I'll see you all next time. Bye team.